Edenheimer. I would also like to mention to you that recording is in process so that any of the attendees can have availability of this presentation at a later date. Also, I'd like to mention that there's a panel on the right-hand side of the screen for questions and answers. If you have any questions during the presentation, type your questions in and one of our moderators will pick it up. I'd also like to note that there will be some polling questions throughout the presentation. I'm personally interested in what you're using today and what your thoughts are about the future of monitoring oxygen. With that said, let's get started. We're going to go through a quick couple of slides on who is sick, and then get into why we measure oxygen, how we measure oxygen, show you some applications and some actual installations, a quick talk about certifications and conclusions with using a tech transmitter to measure oxygen. SICK has one of the broadest portfolios of sensors in the industry. We have sensors that are used in the factory and in logistics, as well as process automation. Our company is in the field of automation. Today's transmitter comes out of our analytical group, but we also have a number of sensors for presence detection in factories, industrial safety around moving equipment, flow measurement in natural gas or in a flare line, and in the industrial application space, the confluence of robotics, programming, the cloud, and Industry 4.0. We have a number of other sensors that are available for systems, motion control, identification, and exploring new business areas continuously. But today, we're going to talk about why we measure oxygen in storage and process and how we do it. We're going to focus specifically on explosion and fire safety today. However, the presence of oxygen can also affect a number of other factors, such as product quality, changes in the polymerization process, for instance, in making super polyamides. Those are the same types of material that are used in Kevlar vests, and the color changes are undesirable in the final product. You also use it in inerting for food and pharma processes, and fermentation or composting, and air separation. So the measurement of oxygen happens all around us every day in almost a myriad of products that would change our lives if it weren't for the ability to measure and control the oxygen content. But today we want to prevent explosions and encourage fire safety. And we're going to do that through inert gas blanketing. There are three elements required for an explosion or a fire: fuel, an ignition source, and oxygen. Through inert gas blanketing, we aim to remove at least one of these three elements, which is the oxygen. In inerting, oxygen is displaced with another gas that has no oxygen in it, and this decreases the oxygen level in our enclosed space until it's at a safe level. What happens if oxygen is present in our process or storage? I think we've all seen this on the evening news. It takes a simple spark or a strike of lightning, and if oxygen is present above the contents of our hydrocarbon fuel, we instantly have a fire and an environmental issue. But it may not be as apparent. It could be in a flow line. What we see laying on the pipe rack in the center of the picture is the tip of a flare. That flare tip should be on the stack behind us about 100 or 150 feet up in the air. But oxygen in the line leading to the flare caused the fire and explosion inside the line instead of outside the line at the tip. On the right, we can see what happens when oxygen gets into our process itself. A large industrial motor lays on top of a several inch in diameter steel line, bending it and pushing it out of position. So how are we going to measure the oxygen? The easiest way is using an industrial laser beam. And By the way, we have a poll here. If you'll answer the poll question, I would greatly appreciate it. It should be on the right-hand side of your screen. In this case, we use a laser beam which has a wavelength range of around 760 nanometers. And the term for this application of lasers is TDLS. More into that later. Now, if we were just using the handheld laser as we indicate above, all we have is a laser beam, but we would not have the ability to make a measurement. What we need is both the laser emitter and we need a detector. But there's no way to get the laser beam to the detector in the top photo. But in the bottom, we have an open measurement cell with a mirror. The mirror reflects the laser beam back to a detector and enables us to make a measurement. This is an extremely fast measurement since we're working with light. It's extremely selective and has no moving parts. Now, what does this look like in application? The measuring principle itself is tunable diode laser spectroscopy, TDLS. What we're going to measure with this technology is the oxygen value in our storage tanks or in a flow line or a flare line. The measuring ranges can be 0 to 5, 25, or 100%. That is field configurable and is usually only set up one time when the application is being installed. Now what we have here is, of course, the sensor and probe and mirror, which we saw on the previous screen. The laser and the detector are at the central part. The mirror is at the far end of the cell. So our laser beam fires to the mirror and back to the detector. Everything is encased in an aluminum enclosure that's IP66 for weather protection. It has an LCD display and HMI to allow us to set it up once we get it to the field, and very simple connections consisting only of a cable for power and a grounding pin. Now, the principle that this is measured on is using a laser or a light beam. And historically, the entire spectrum was utilized to make a measurement. Changes in the pattern of the entire spectrum were utilized to determine what we were looking for in the chemistry of the sample. As we moved forward with more sensitive and better equipment, we were able to make these measurements. My apologies. I should have turned on my camera earlier. As the technology improved and we had more sensitivity and better optics, we were able to use a very narrow wavelength of light and look at the pattern or individual peaks in a narrow band pass. With a laser, we're actually able to focus on a single peak. And by looking at a single peak and measuring the amplitude of the peak, we're able to determine the oxygen concentration in our sample. Being that this is a very narrow bandwidth, it is extremely selective. So we have very few and very minor background effects. Again, it's a fast measurement, and did I mention that it has no moving parts? So based on this, we actually have several mounting options to allow us to adapt this to different process environments. The in situ version, which is seen at the top, has simply the measuring cell inserted in and directly exposed to the sample stream. The extractive sample cell version has the sample cell encased in an enclosure which allows us to flow the sample in and out of the surrounding cell. And this allows us to make adjustments in the application. The in situ is mounted directly into the sampling point, requires no sample system, and has an extremely fast response. The extractive sample cell, if you choose to go that way, allows you to compensate for pressurized or high temperature applications. A simple sample system is all that's required to provide control of pressure and temperature, and it's ideal for replacing problematic older analyzers that may be paramagnetic principal or electrochemical cells. Our version of this is referred to as a SiC oxygen transmitter. Transit. Here we can see an in situ version of the cell. We have on the top the first of two redundant units that are installed in the vent line on some storage tanks. As you can see in the bottom example where the transit has yet to be installed, there is a process flange that's attached directly to the pipe. There is an instrument flange which is mated to that, and it has some mounting screws and a through hole to allow the probe to be installed directly into the process line. That's accomplished by putting in an instrument flange adapter that has appropriate seals to seal the sample in and the atmosphere out. Sometimes when you're making an in situ measurement, there can be undesirable materials in the sample flow. Sticks and stones, or water as I refer to them, can be present in almost any process. So we provide either a screened mesh or a hydrophobic PTFE filter, Teflon filter, in addition to the screen mesh to repel water and solids that may be entrained in the process flow. These filters can help by allowing you to make the measurement in situ, save on expensive sample conditioning systems, and also provide simple exchange for customers to maintain their own stock and replace these in the field on a routine schedule if needed. The other method of installation is an extractive application. As we can see here, the entire oxygen transmitter with the appropriate cell is mounted on a sample panel. Depending on the application itself, we can control the pressure and temperature by bringing the sample to the panel. We control the flow and even indicate whether there is positive flow or not. We have an adductor if it's low pressure. We can allow a stream of nitrogen to pull the sample through the adductor and back to the process and make any electrical field connections which are necessary. In this case, we can see an extractive setup on a toluene storage tank. Our sample panel is located just below the transit itself, and you can see the appropriate size of the system. It's very small, it's very compact, it can be mounted anywhere in your process, and judging by the size of the technician here, you can see it won't take up much space. Here's another installation. We can see our simple panel. We can see the transit itself, which has a protective blanket put over it to allow protection from the sun and elements, but it is an IP66 case, so it is water resistant. In this particular case, the customer was interested in evaluating new technologies. So there was previously an electrochemical cell mounted in this process. They chose to mount a TDLS and some paramagnetic solutions. In this case, the paramagnetic solutions were two in parallel. They ran this for 30 days and tracked the results over that 30-day time period. As you can see, this 36-hour time period, after about 24 hours, the electrochemical cell started to exhibit errors. The paramagnetic analyzers and the TDLS tracked each other very well and showed very little perturbance in the measurement itself. At the end of the 30-day time period, the customer chose to go with the TDL technology. Due to the simple installation, it did not require a sample system. In this case, it was simply mounted in the flow stream going to the rest of the analyzers. And without the cost of the sample system and the simplicity of the installation, it made it an easy choice for the customer to go with TDLS. I would like to point out that the transmitter is area classified in the Canada and in the US. It also has ATEX certifications. In the US, we are FM approved. It meets Class 1 Division 2 on the electronics enclosure, groups A, B, C, and D. And inside the process, the laser itself is non-incendiary. So it is Class 1 Division 1 or Division 2 and Division 2, groups A, B, C, and D. The FM approval is tagged on every analyzer. So in conclusion, what does TDLS offer? Excellent long-term stability, only requires calibration on a yearly interval. Potentially extreme cost savings due to no samplage system, minimal consumables, and a minimal sample system if one is needed, in addition to, as you just saw, an extremely robust measurement. You have a choice. In situ measurement, very fast measurements right in the process, low operational costs, or an extractive measurement. Easy to install, close coupled to the process, a very simple sample system that just controls temperature and pressure. And it's based on the transmitter concept. So it's very easy to operate, minimal maintenance required, and has a 4 to 20 milliamp and a single diagnostic output. Finally, it is FM certified to meet EX certifications. So it's a perfect installation in a chemical or refining environment. With that said, that's the end of my presentation. I would open it up for any questions.
Hey, Paul, I've got a couple of questions here if you're ready for that. The first is, how do you calibrate in situ applications?
In situ installations, you can accomplish both a zero and a calibration through flooding the sample cell through a calibration port. On the bottom of the analyzer, there is a gas port. You can hook that up. If you have the Teflon membrane into place, that offers you the opportunity to flood just the sample cell, and it will permeate out of the sample cell eventually and be swept away into the process or to a low pressure waste drain.
All right, great. And we have a few more here. Next one is, okay. Are there any cross sensitivities with the measurement?
There are some cross sensitivities with the measurement. Typically, we have a question and answer sheet that goes to the customers before the installation. A detailed examination of the sample environment is conducted through that question and answer sheet, and we can make small adaptations to account for any cross sensitivities that may exist in the sample. In most samples, there will be little or no cross sensitivity.
Okay. Next one's a multiple parter. So let's start off with the first one here. For a storage tank application where oxygen must be kept between 6 to 9%, are you aware of gases stratifying if well mixed? Oxygen/nitrogen stream blankets the tank.
Because many of the tanks are live, I have not seen stratification in the tank. In other words, they're always being swept with a purge gas, and the volume of the tank is changing on a routine basis. So it's increasing when it's being emptied and filled, decreasing when it's being filled. What I have seen on a couple of occasions are a long dead space between the tank and the sensor. It's not uncommon for people to take the most convenient place for installation, and on one particular tank, we saw an upright 6-inch process pipe that made a 90 degrees after about 4 feet, and after another 4 feet ended in a process flange. So we basically had about 8 feet of dead leg. The transit was installed at the end of that 8 feet of dead leg. As we thought might happen when we did some simple testing, in other words, flooding the sample probe and waiting for it with an inert gas and waiting for it to come back to the tank volume, tank concentration, it took almost 24 hours for diffusion to get the headspace contents out to the transit itself. So you do have to be careful. Look at the sample point, look at the turnover in the tank. I imagine stratification can be an issue, and we can certainly have one of our installation experts come out and take a look at that and give you some advice at the installation time.
Great. And there was a second part to that question, but I have to apologize to the attendee. It got cut off, so I'm not sure exactly what the remainder of your question was, Paul. Hopefully we can provide your contact information once we get through the rest of the Q&A so that anyone can contact you if necessary. But we do have a few more questions if we could move on to those. The next one is, can this be used in a boiler exhaust for combustion control?
I would like to ask one of my experts that's online here on my panel with me. I have not used it in that application. John Chitty, do you have a comment about that?
John, I've unmuted you if you'd like to speak.
I think that's John Chitty or John Callum.
Yeah. Hi, this is John Chitty. Can you hear me now?
Yep.
Yes, sir.
Oh, okay. Certainly it can be used extractively, although that's not a traditional application for it. That's your response time would be delayed because it would be an extractive analyzer. That's probably more appropriate for zirconia oxide type of in situ measurement. But if it is extractive, we can measure it. We just have to control the temperature and the pressure that the unit sees. It is somewhat limited in that respect. I hope that answers this.
I have a further comment. This is Matt Diggs. Excuse me. Yeah, that would not be an ideal location if it was at the exhaust, like where your SIMS measurements would be. You really want to be closer to the firebox and speed of response for combustion efficiency, combustion control. So the key word there is, and the question was, in the boiler exhaust. I think you really want to be closer to the firebox.
All right.
Okay,
Thank you,
Eric,
panelists.
next question.
Sure, we do have one more question so far. Do filters impact the response time?
Absolutely, they do. The most ideal situation is to have no filtration and just a sample flowing through the sample cell, which is open on all sides. And that gives you almost instantaneous response. Adding the screen will add a small amount of time to that, so you might have 10-second response. And adding the PTFE filter, which I believe is something on the order of 300 microns, will give you about a 60-second T90 response time. So it depends on the speed of flow through your system. The higher the flow rate, the less the T90 is.
All right, great, Paul. One more has come through.
Right.
How minimum? The question is, how minimum range can it used? I'm sorry, this is maybe I'm reading this wrong, but it says how minimum range can it used ppm?
believe the minimum range is 0 to 1,000 ppm. Somebody can correct me if that's correct. The range itself, I think, is 0 to 1%. And then the minimum detectable range is in the 0 to 1,000 ppm range. If anybody has an exact number on that, please let me know.
Great. Okay, that was the last question. If the audience has any others, feel free to enter those here. Otherwise, it looks like Paul's putting his information up on the screen now.
Sure. So you can reach me, my email address here at sic.com. Feel free to call me on my cell phone. And if we don't have anything else, I would like to encourage you to join us next Tuesday for our next Tech Tuesday presentation, ultrasonic meter diagnostics, what does the future look like? So we'll be giving that in 2 weeks and look forward to having you join us. Thank you.
Thanks, Paul. And just one more reminder for our audience, we do have a $50 drawing for all customers who attended today. So that'll be an Amazon gift card, and you'll be notified in the next few days if you're a winner. Thanks again, Paul.
Thank you. Thanks for joining.